Everyone, my name is Zhenyang. I'm from University of Waterloo. Today I'll be presenting our work, pushing the limit of 1-Minimality of Language-Agnostic Program Reduction. Debugging language processes such as compilers is usually a difficult task. A popular compiler often receives many bug reports from its users and developers. And to reduce the workload required for fixing these bugs, maintainers of many language processors explicitly encourage bug reporters to submit a minimized bug report, to submit a minimized bug triggering test case. For example, here I quoted some sentences from some of the most popular compiler communities, including LLVM, GCC, and Rust. And we can see all of them encourage to provide a minimal test case. And program reduction is a technique that can automatically minimize bug triggering programs. And this figure shows the task of program reduction. So as we can see, a program reducer will take two inputs. One is the program that has the property psi, and the other is a checker that can check whether a program has a specific property. And then the reducer will finally output a minimized program, which still has the property. And to apply program reduction to test case minimization, you can simply use the original large and complex bug triggering program as the input program, and then set the property to be that the program triggers this specific bug. And then the reducer can produce a minimized program that can reproduce this bug. And program reduction is a trial and error process. During the reduction process, a current best program will be maintained, and it is initialized by the input program. And in each iteration, the reducer will perform a transformation to the current best. For example, it may delete some code from it, and the variant will be obtained. And then this variant will be checked to see whether it still has the property. And if not, the reducer will generate another variant by applying another transformation. And if it passes the property check, then the current best will be updated with this variant. And the entire process will terminate if no variants that have the property can be generated by any available transformations. So Perses was the state-of-the-art language-agnostic program reducer. It is deletion-based, which means it only tries to remove tokens from the program. And meanwhile, it is tree-based, which means it performs reduction on the tree representation of the program. Specifically, you will first pass the program to get the path tree, and then try to delete nodes in the path tree in a top-down manner. And most importantly, Perses can ensure 1-minimality, which means that in the result produced by Perses, any single node cannot be deleted. So for program reduction, finding the global minimum is NP complete. Therefore, 1-minimality was proposed as a relaxed goal for program reduction. And the 1-minimal result can be actually considered as a local minimum. However, there can still be many reduction opportunities in a 1-minimal result. Here is a real-world example. This program on this slide actually can trigger a bug in LLVM. And these two statements that have the shift operations are the key to trigger this bug. And this program is the reduced version output by Perses. So it is 1-minimal. However, we will see that there are still many reduction opportunities in such a reduced program. So first, let's look at this highlighted code. We can see that this program, these statements passes the value of ID 0 to ID 6, and then to ID 7, to ID 8, and eventually to ID 1. So we tried to replace the ID 8 highlighted in yellow with ID 0. So the program directly assigned the value of ID 1 to ID 8 to ID 1. And we found the program after this replacement will still trigger the same bug as expected. But notice that after this replacement, the three statements highlighted in red becomes redundant. So we deleted these three statements, and still the program can trigger the same bug. So now we've already got a smaller result, but we can make it even smaller. So let's look at this typedef statement. This typedef statement defines an alias for the type short. And this alias is used once, which is highlighted in yellow. So if we replace the alias with short, then the typedef becomes redundant and can also be removed. And finally, we also found that if we remove the highlighted for statement and the keyword else at the same time, the program will still trigger the same bug. So from this example, we can see that there can still be many reduction opportunities in such a one-minimal result produced by the state-of-the-art. And to further reduce a one-minimal result, we can perform some non-deletion-based transformations to the one-minimal result and possibly make it not one-minimal. For example, we can change some identifiers or specifiers as shown in our example. And also, we can perform a more exhaustive reduction algorithm. For example, remember that in our last step, we removed the for statement and the keyword else together. And such a reduction opportunity can be seized if we try to remove every 2 nodes rather than just 1 node in the path tree. So based on these observations, we propose a framework called Vulkan. And this figure illustrates the typical workflow of the tree-based program reduction. And on top of this, Vulkan introduces a set of auxiliary reducers to help further reduce one-minimal results. Each auxiliary reducer performs either a certain type of transformations or a more exhaustive reduction algorithm. And once a one-minimal result is obtained by the main reducer in our framework, one of the auxiliary reducer will be invoked to produce either a smaller or a transformed result that still has the specified property. And this smaller or transformed result will be sent back to the main reducer for further reduction. And we propose 3 example auxiliary reducer based on our observations, and more reducers can be actually added to this framework. So recall that in the previous example, we successfully removed more code by replacing an identifier with another identifier in the program. Therefore, we propose an auxiliary reducer to perform identifier replacement. So this reducer will first extract all the distinct identifiers in the program. And then it will choose an identifier, for example, ID 0, and try to replace all the ID 0 except the first one with another identifier in the program. Here the reason to keep the first one is that the first identifier usually appears in a definition or initialization. If all the following usages of this identifier are successfully replaced, then this definition or initialization will become redundant and thus can be probably removed. If this replacement makes the program no longer trigger the bug, this auxiliary reducer will try to replace it with another identifier. And if all the other identifiers have been tried, it will try to replace the next identifier, for example, ID 1. And eventually, it will find that if we replace the ID 8, highlighted in yellow, with ID 0, the resulted program can pass the property check. And this new program will be sent back to the main reducer, and the main reducer can further remove these redundant statements. And also recall that after this, we further reduce the program by replacing the alias with short. So we implement another auxiliary reducer called subtree replacement to perform this type of transformations. So this auxiliary reducer tries to replace a subtree in the path tree with a new one. For example, it may try to replace the subtree that corresponds to the highlighted alias. The subtree is shown on the left. The new subtree will be generated based on the formal grammar. For example, here we have the production rule of type specifier in the C grammar. And this rule basically shows what a type specifier can be. And with the guidance of the grammar, a new valid subtree can be generated and used to replace the original one. And finally, in the previous example, we also found that we can remove the for statement and the keyword else at the same time. To make such reduction possible, we proposed the third auxiliary reducer called tree-based local exhaustive enumeration. So here on the right side, we show the tree structure of this if-else statement. This reducer uses a sliding window with fixed length. We set the default length to 4, and the sliding window will move from left to right and top to bottom in the path tree. And for each position of this sliding window, the reducer will enumerate and test all the possible variants obtained by deleting elements in the window. For example, when the sliding window is on the leftmost, as shown by this blue box, the reducer will generate 11 variants by deleting elements from the window. And after test all the variants, the sliding window will move by one node. And when the window moves to this position, it will find that the for statement, which is statement 2, and the keyword else can be deleted together. This auxiliary reducer is inspired by a reduction algorithm in C-reduce. C-reduce is a reducer that's specifically designed for C and C++, but it also contains some language-agnostic reduction algorithms. The algorithm in C-reduce is list-based, and here we improved it by making it tree-based. And eventually, with Vulkan, the example we just saw can be reduced from 116 tokens to 56 tokens. To evaluate our approach, we implemented a prototype of Vulkan on top of Perses, and we used Perses as the main reducer in Vulkan. And we conducted extensive experiments with a multilingual benchmark suite, which contains 20 C programs, 13 Rust programs, and 93 SMT programs. And we choose Perses as our main baseline since it was the state-of-the-art language-agnostic reducer. And we also use C-reduce as our baseline in some experiments. First, we use these 3 tools to reduce the 20 C programs. And the statistical results are shown in this table. From the table, we can see that Vulkan produced smaller results than Perses in general. On average, the results of Vulkan are 35% smaller than those of Perses. And in this experiment, C-reduce is still the best. But this is expected because C-reduce is specifically designed for reducing C programs. However, interestingly, we found that if we use Vulkan to reduce the program output by C-reduce, we can even get smaller results. We also ran experiments with Rust and SMT benchmarks. In these 2 experiments, the results of Vulkan is 27% and 52% smaller than those of Perses. In terms of efficiency, Vulkan inevitably requires longer execution time. It is around 2.5 times slower than Perses in C benchmarks, and for Rust and SMT benchmarks, which generally take less time to reduce, Vulkan is 7 and 8.5 times slower than Perses. So to sum up, Vulkan can reduce more tokens than Perses. It actually trades off the efficiency for smaller reduction results. And also, like Perses, Vulkan is language agnostic. It is effective with different programming languages. And that's pretty much about my presentation. Thank you for listening. I'm happy to answer any questions.
So I have 2 quick questions. So first is that you talked about this identifier replacement.
Yeah.
So once you do the replacement, how do you test? What is the property pass thing? Like, what are you testing? That they're equivalent programs, or?
Sorry,
So my question is that when you do this identifier replacement,
yes,
you get a new program.
you're right.
And you said that this passes the property.
Mm-hmm.
So what's that property?
Okay.
I missed
so the property is always that the program can trigger that specific bug.
So it's not the program are equivalent. They can trigger.
No, it does not need to be equivalent. It just have to trigger that specific bug.
I see. Okay. The second question is about. So in the example, like you had this successive assignment, and that you said that you can remove.
Yes.
So why don't you start from there and just find the successive assignment and then remove them? It might be a stupid question, but that's something which came to my mind first, that if you have ID1 equal to ID2, ID2 equal to ID3, something like that, then why don't you just do it initially in a pre-processing?
So we want this process to be like automatically done. So I'm not sure like how.
Because wherever you're removing these lines, it seems like a successive assignment, like just a.
Okay, if you like directly remove these statements without the replacement, then the program will no longer trigger that bug because it might be like rejected by the compiler in the early stage. Because, for example, the ID8 is not defined or something like that, and the bug may be at the, for example, following stage of that compiler. So if you directly remove the statements.
All right, thank you.
Yeah.
Thank you.
I noticed that both of the examples you had for the C program had sort of like the flavor of like just general compiler optimizations. I was wondering if you like looked at for like some adding other rules that like have an optimization flavor to them, whether that's like constant folding or something, and if those perform better than other rules.
Sorry, I didn't get your question.
Like in removing the assignments, like I would expect an optimizing compiler to do that, like once it's a lot further down the pipeline. But
Okay.
like that seems like a fruitful way to minimize programs in general. Are rules that look like that better than other rules, I guess? They like have this optimization-y flavor.
So
Or
what,
did you look at that at all?
sorry, I still didn't quite get the question. Maybe.
We can talk about it offline.
Okay, yeah. Sorry about that. Thank you.
I'll make it quick. Hi. Do any of your transformations do function inlining? I know that we've found that to be useful in reducers that we've built before.
Function, you mean use function line to minimize the program?
Yeah, like you have a function that's called in one place, so you inline the function body and then do further
Yeah.
reduction.
Okay, the point here is that we try to make the tool language agnostic, but like function inlining is kind of hard if we don't have any knowledge of that specific language. Yeah.
Okay.
Okay, thank you very much. And let's have one last round of applause for all of our speakers.